So I'm starting, Anilji.
Yes, please. Yeah.
So good morning, everyone. I am Gaurav Gupta, Manager Design. First of all, I would like to thank you, Team DMRA, specifically Anil Patel sir and Mahesh Sareen sir, Chief Engineer Design, for giving this opportunity today to present on the topic design of various aspects of underground stations. And I will be covering stations, tunnels, and cross passages. So I am going to start the presentation.
My one your
I hope my screen is visible to all.
Yes, yes, it is visible.
So this is the basic content which I will be covering all the briefly the design aspects of underground stations, the structural elements of underground stations, types of underground stations depending upon their construction methodology, then design of underground station, then bored tunnel, design of segment lining, and cross passages and NATM tunnel. So firstly, we will move on to the underground station. So what basically is an underground station? It's simply a structure to assess the metro facility beneath the ground level. Now, what are the various structural elements in underground stations? These I will tell you one by one. And I have divided these elements of structural underground station in two parts. First one is permanent elements. As the name suggests, the permanent elements will be those which will be there for the whole design life, which is 100 years. And next comes the temporary. Temporary elements are the components in an underground stations which are there only to assist the construction, like during the construction stage of the project, which I will be telling you in the next slide that what are the temporary elements. These temporary elements will not be there for the whole design life of the structure. These only will be there to aid the construction process. So firstly, we will move on to the permanent elements in underground stations. First comes the diaphragm wall or a wall. Now, diaphragm wall, what is a diaphragm wall? Diaphragm wall is a wall which is built basically in top-down constructions. Uh, and a wall is a wall which is basically constructed in a bottom-up construction. Then comes the roof slab, then the concourse slab, base slab, all the permanent elements. Then comes the platform slab, then comes the columns, then comes the pile and tension pile, then comes the all the staircase and other internal structures. These are all the elements which are going to be there for the next 100 years for the design life. Now this is a cross section showing all the permanent elements in an underground stations. You can briefly see here that there is a diaphragm wall, a roof slab, and then concourse slab, and then a base slab with a pile and platform slab, permanent column you all can see in this cross section. Now, what are the temporary elements in an underground station? First comes the pile, which are the different types of piles: secant pile, soldier pile, and contiguous pile. Now, this is very important in the temporary elements, that which type of pile system we have to use in the at our construction site. So firstly, we will one by one, I will tell you what are the difference in this system. First comes the secant pile. A secant pile is the uh, system of pile of primary and secondary piles, in which you can see in the diagram I have shown that they are the like primary pile is overlapping the secondary pile system. So basically, it is an watertight structure, and secondary pile is a system of pile where we have the reinforcement cage inside. It is basically an RCC pile, and the primary pile is only the concrete pile. Now comes second, the soldier pile. Soldier pile is a system of pile in which steel eye section is uh, uh, like embedded into the ground for the retaining wall structure, and then it is overlapped with the wooden lagging. Like in the spacing in between the spacing of the soldier pile, we install the wooden lagging system. Then comes the contiguous pile system. In contiguous pile system, there are board piles similar to that of the secant pile, but these piles are not overlapping to each other. So what is the difference between these piles, and how to ensure that what type of pile retaining system we have to use even in our construction site? So benefit of using secant pile is that wherever our groundwater table is at uh, higher level, like if the groundwater is at ground level only, then we have to adopt the secant pile system because it is a watertight retaining structure. Like if we use soldier pile system or contiguous pile system in the ground in the soil periphery where the ground water table is high, then there are chances of water ingress into our excavation site. So in shortly, the secant pile system has to be used where the groundwater table is higher, and we can use soldier pile or contiguous pile system where the water table is lower than our excavation level. In that scenario, we can use the soldier pile and contiguous pile system. Now, if we come to the economy, like even if the water table is lower, why we have to adopt soldier pile or contiguous pile system when we have a robust system like a secant pile? But then comes the economy, because the secant pile system will be costlier than the soldier pile or contiguous pile system, because in soldier pile system there is steel eye sections which are embedded into the ground, and after their use is over, like after the soldier pile system is there at the site for 4 years, then the contractor can remove the soldier pile system and can use the I sections elsewhere later on the project or at another project. Now comes the second element in temporary elements is strut, and then comes the veiler. Like this is a plan showing a typical strut and veiler connection. Now, what is a veiler and what is a strut basically? Whenever we have installed our retaining system, which can be D-wall in top-down construction and secant pile or soldier pile or contiguous pile in bottom-up construction, whenever we do the excavation, that excavation, the retaining system has to be supported by the veiler and strut system, so that the whole of the system is in balanced state. Otherwise, only if we can install the soldier pile or retaining system, uh, there will be deflection in the retaining structure. So to control the deflection and to control the bending moments of the uh, retaining wall or retaining structure, we have to install the veiler and strut system, which I will later explain. In the diagram, you can see a veiler is a steel eye sections which run along the length of the station or a curtain cover, and strut is a perpendicular member to the veiler, and you can see diagonal strut also in the system, which is at 45 degrees from the veiler to the strut. Next comes the plunge column in temporary elements in the underground stations. Now, what is a plunge column? Plunge column is basically a temporary column made from the I sections. Uh, they can be two ISMBs, two UC sections, and inside that there can be a sand filling or concrete filling also, depending upon the design requirement. Now, what is the requirement of a plunge column? Plunge column will support the roof slab in the construction stage. Whenever you are going to the top down constructing a station in top-down construction, there will be a requirement for the roof slab to get support from somewhere, because the permanent columns will always be casted in later on in bottom-up construction. So the plunge columns are casted till the permanent columns are there at the site, and these can be at any locations. Like in some of the projects, the plunge column can be converted into a permanent column also, or the plunge column can be alternate to the permanent column. That all depends upon the design and site conditions. Now I will tell you about the types of construction methodology for underground stations. Like all the basic elements I have explained you. With that, now you will be to appreciate the what are the construction methodologies in the underground stations. First comes the top-down construction. From the word itself, it's very clear that when the construction of permanent structure, that is the roof slab, concourse slab, base slab, is done from top to bottom of the basement together with deep excavations, is called the top-down constructions. For better understanding, I will show you a video for the top-down construction. Now, this is the guide wall. Now, what is a guide wall? It is also a temporary element which is used to guide the construction of the, like when the auger of the like diaphragm wall is have to be start the excavation. The guide wall will help in guiding that to maintain the verticality of the d wall. So this is the first step of the construction of before the d wall. The guide wall has to be constructed.
वॉल्यूम क्यों नहीं है?
इसमें आप देख सकते हैं जैसे कि here the strut and velar you can see there is the longitudinal member along the length of this curtain cover is the velar, and then the perpendicular member is the strut, and this diagonal strut is called or is also called splay or diagonal strut. So this was the
Guruji, Anil, but stuff. Can we take our on one query?
yes, yes.
Someone has asked in contiguous pile, what is there in between two piles? You have shown contiguous pile. So
Yes,
some.
there
So
there there is shotcrete between the two piles.
okay, I hope this answer the query. There is a shortcut in between two piles when you go for contiguous pile. Okay, thank you, Gaurav. Please continue.
I hope everyone was clear from the video about the top-down constructions. Any doubts, like you can ask so that I can move further. So I hope everyone is clear. Like now, I will show you the drawings of the typical construction reference drawings of the construction sequence drawing of the top-down construction. The same, the construction sequence which was shown in the video, like a design is prepared for the execution of this method. So we can see one by one that there is a stage one in which the barricading as per specifications to cordon off the working area. Then the utilities shall be diverted, if any, from the station area. Then the construction of the guide walls. Then the construction of the diaphragm walls with coupler left to provide connections with the slabs. Then the installation of the water stop and the pile, temporary steel column, which is plunge column, and the pile below the base slab. After the construction of the D wall, then we will move to the construction of the roof slab, as you can see in the stage 3. Then after we construct the roof slab, then we can further excavate the soil up to the level of concourse slab. You can see in stage 4, the this shows that the soil has been done up to the concourse slab. Then we can cast the concourse level slab. Then similarly, we will start excavating up to the base slab, and then we can cast the base slab. So simply, first the diaphragm wall will be constructed, then the roof slab, then the concourse slab, and then the base slab, and then the permanent column. So this method is called the top-down construction. Now we move to the bottom-up construction. Now, what is the bottom-up construction? When the construction of permanent structure is done from bottom to top after completion of the deep excavation of this area with the temporary supports. Now, for this also, I will show a video so to have a better understanding of the bottom-up construction. As you can see here, firstly, the soldier pile system has been installed, and at one side, contiguous pile system has been installed, and this is the basically temporary retaining structure of the for the soil, and then we have the started the excavating the soil further down. These are the installation of the valers. These are the installation of the splay, which is also called diagonal strut. This is the straight strut. Now in between this, you can see these are the plunge columns, which will also, or you can also call them king post in this case, because they are also supporting the strut to reduce the span of the strut. Now, after a first layer of the whole support system has been installed, which is the strut and villa, the excavation has been done up to that level. After the first level is achieved, then we move down to the second level of the strut and villa. Now, after like we have constructed after we have excavated up to the base slab level, then we have casted the first casted the base slab, and then the bottom of wall, and then the concourse slab or roof slab. Similarly, for bottom up constructions, this is the a typical construction sequence drawing in which firstly the barricading has been done, and then our support system has to be installed, which can be any diaphragm wall, secant pile, contiguous pile. Then we are installing the veiler and the strut with the king post. Then we are moving down to the base level, and then we construct the base slab, and then the bottom of wall, and then the roof slab. I hope it's clear to everyone the construction sequence of top down and bottom up.
Yeah, Guruji, can we take a few queries now?
Yes, sure.
Uh, so there is another query. When someone has asked when it's decided to go for top-down construction method. It's a basic query, I think.
It's very basic query, like the type of selection of top down construction or bottom up construction depends upon the numerous factors, like the space of the site. Like if the space is very restricted, like in Delhi, mostly there is no space, working space available in the area which where station has to be built, then we go for the top down construction method. And where if we are like building a station in the park, like in phase 4 we have built DC6 Krishna Park station in the park, or Deraval station in the DC5 project. If the space is available, then we can go for bottom up construction, but if the space is very constrained, limited, then we have to go for the top down constructions. And why? Because like in top down construction, our temporary wall and the permanent wall will be same, so the area will be less required. Because if we go to the bottom up construction, then the temporary retaining system has to be casted beyond the wall area. So we require the station width, like it is 22 meters. Then in bottom up construction we may require 28 meters of width. And if the station area is available for construction is only like 25 meters, then we have to go for the top down construction also. And the other reason can be also the economy, and that depends upon the situations. Like sometimes the area is also available, and for the like time also is very important. If we have to go for the top down construction, it is faster a little bit. And then it also depends upon the geology of the soil. Like if there is rocky strata, then the grabbing in the rock strata is very difficult, because the grabbing is only possible in the soil. However, like rock like there are grabbing machines for rock also, but it is very time consuming. So in that cases we go for bottom up constructions, because we construct the secant pile firstly, and then try to break the rock with the breaker or by controlled blasting.
Thank you. You have nicely explained this query. Next question is basically someone is asking regarding tolerances associated with the wall. I think tolerances regarding verticality or something. I think it is already mentioned in all outline construction specification.
Yes,
We will
yes,
share
it's
this
mentioned
document.
in OCS. Yes.
Yeah, we will share that document. And someone has asked for explain the sequence of removing strut veiler. I think it is pertaining to execution topic. So we will cover this, I think, in next webinars which we have planned on 19th. So we will discuss construction aspects. In that, we will discuss the sequence of installing the veiler and strut and then removing it back. I think no need to discuss here. But yeah, Someone has another question that up to what depth the guide wall to be installed? Is it equal to depth of the wall? This is a query
No,
to you.
no, it is the only 1.5 meter maximum. The depth of the guide wall is 1.5 meter maximum and thickness is roughly around 300 mm. The D wall
Perfect.
will move towards the like 5 meters below the base slab. Like the if the base slab is 20 meter from the ground level, then the D wall will move up to the 25 meter, 26 meter as per design. But the guide wall will only be restricted to 1.5 meter.
Thank you. Thank you, Gaurav. I think query has exhausted now. You can move ahead. Thank you.
Okay, I will restart the presentation. Now we come to the main part of our presentation, which is the design of underground station, structural design of an underground stations. So I will try to cover all the basics which everyone should know in the structural design of underground stations. Firstly, the structural design of an underground stations is done like for the permanent elements is done in 3D FEM modeling in structural software like StatPro or Midas Gen or any other similar software for permanent stage and Wallop or Plexus or Phase RS2 for temporary stage analysis. There are two types of stages in design also, permanent and temporary. Construction stage, which is a temporary element, construction stage, and service stage, which will be there for 100 years. Then application of the material properties and application of loads and load combinations as per the DBR or ODS. Then comes the analysis of the structural model. Then comes the design of structural components. And then comes the drawings of the structural components for which the drawings has to be issued to site for the construction. So one by one, I will be starting with the construction stage analysis. Construction stage analysis is done basically in software called Wallop. So Wallop allows to simulate the construction stage-wise excavation with installation of temporary strut, permanent slab, top-down, and even installation of surcharge loads. Now, what is special about this software is that this software enables you to have the soil structure interaction between the soil and the structure. Like in construction stage, whether it is top-down or bottom-up, there has to be a construction sequence where we will excavate the soil and then we have to design the support system which I have already explained you. So now we want the forces and the moments for which the we have to design our retaining system and strut and vellum. So Wallop is a software which enables us to do this. So I will explain you this in the model itself. So basically I have this Wallop software you can see, and then I will show you example of our phase 4 project. Firstly, what you have to do is that you have to define the strata. Like you have to, you can see here, we have to firstly provide our ground level. So in this case, our ground level is at 211.83 meters. Then we have to define our strata layer wise as per the approved GIR. So in this, I have pre-feeded the data. It shows that from 211.83 to 209.117, there is one kind of data. And then similarly, up to 33 or 44 meter difference, the soil strata is changing. So I have defined that how many types of soil strata are there in our uh, uh, like soil. So now we will define the parameters as per the GIR. So in the first layer, I have defined that it is the soil fill. So I will define the bulk density, Young modulus, and the coefficient at rest, which is K naught, and that whether it is overly consolidated or normally consolidated soil, and then Ka and Kp. and these all will be as per the GIR. We have to just input the data which we have got from the geotech engineer and the GIR report. You can see here the data has been pre-filled. Similarly, for like I have defined the 6 layers of the soil strata. So you can see after those we have defined the soil in our system, then what we have to define next is the, now we have defined the ground level and the soil, then comes the water table. So what is the ground water table at the construction stage? So that also comes from the GIR. So here in this case, like we have defined that the water table, initial water table at the site is 204.27. So roughly around 7 to 8 meters below the ground level, we have defined the soil. We have defined the water table. Then after defining the water table, we have defined the uh, water pressure profiles. Now, what is this system? You can select like if fully embedded wall. Like if you are proposing a diaphragm wall in your system, then you have to select the fully embedded wall. Or if you are doing a bottom-up construction, then you have to define like whether it is soldier pile wall or a single pile. So in our case, it is a fully embedded wall. You have to give a elevation of a toe wall. Like from experience, you can give the elevation of a toe wall 5 meters below from the base slab level. So, but this depends upon the iteration only. From this only we will do iterations, and then we have to come finally at the elevation of a tower level. Then we provide the Young modulus of the concrete, moment of inertia as per the thickness. Then we calculate the EI per unit length of the wall. Now comes the important part, like now we have a soil system now and a D wall diaphragm wall system. Then we have to provide the struts. Now, struts can be, what is a strut? A strut is a thing which will support the retaining wall structure. So, in case of a diaphragm wall, in a top-down construction, the main slabs, which is uh, roof slab, concourse slab, and base slab, will also act as a strut only. So, we have to define the parameters for that. And if in a top-down construction, if these are not sufficient, like if the deflection in this case is exceeding in the diaphragm wall from these also, then additional steel strut may also be required. So in this case, we have defined the roof slab level, like this is the roof slab level in this system, 210.58. Then the strut spacing is 1 meter because it is a continuous roof slab. Then we have to provide the strut spacing as 1 meter. Suppose if it was a steel section and a steel section, so it was must be spaced at something like 4 to 5 meters. Then we have to define the strut spacing accordingly. Then comes the area of the strut. Like in this case, the thickness of the roof slab was 800 mm. So the area of the section is zero point 0.8 into 1, so zero point 0.8 meters square. Then we have to provide the Young's modulus. Then we have to provide the free length. Now, what is the free length in this structure? The free length will be the width of the station width, will be the like width of the slab will be the free length of the strut. So similarly, we have provided then after roof slab, the concourse slab. We have provided the strut 204.84 level. Area of the strut concourse slab is 0.55 because the thickness is 0.55. Similarly, we have defined the base slab as the strut. Now comes the loading. Now, what is this loading? The Wallop software will automatically create the soil pressure. Like we have defined the soil types, this will automatically be converted into pressure. Now, this load is the load which will act as a restraint. Like this is the we have provided the roof slab and concourse and base level as our strut system. So they will provide rigidity to the diaphragm wall system or a retaining wall system. So we have to provide the parameters also similarly. So for every slab level, like for the roof slab and concourse slab and base slab, we have to provide the moment restraint from after calculating from the structure. Now this will provide the rigidity and create a fixed end moment in the system. Now comes the surcharge. Like surcharge is, what is the surcharge? As per the ODS, the minimum surcharge has to be 24 kPa or as per the design Like if we have a nearby building near our support system, then we have to calculate the surcharge accordingly. So in this case, we have defined the surcharge as 24 kPa. So now we have defined the soil strata, type of our retaining system. We have defined the water table. We have defined the struts. We have defined the moment restraint. Now we have to apply the construction stages. The construction sequence, which I have told you in the video and the drawings also. Now we have to create in the software. So apply water pressure. So what will happen? The first, there will be a water pressure at the 04.27 level. Then there will be surcharge application. You can see in this bottom right corner that water profile. Then surcharge is applied at the ground level. Then excavation up to the excavation is roughly around wherever we have to construct the our strut. It shall be 500 above the top of the roof slab. So accordingly, excavation till 210.08 on the passive side, then installation of the strut system, then application of the moment restraint, because this ensures that our system is the roof slab is casted at this time, where this pink arrow and a moment is shown. This is I am showing for the top down construction. Then again, the water table is lowered. As we move down the excavation, the water table has to be lowered at the passive side. Then we excavate up to the top of the concourse slab, 500 of above the concourse slab. Then similar again, we install the strut action and the moment restraint at the concourse slab level. Then similarly, we will lower the water table profile, and then excavation at 199.73, which is roughly around 500 above the base slab level. Now installation of the similarly base slab. So this is basically a construction sequence which we have provided. So what we have done basically, whatever was the construction methodology or the parameters or all the loads we have provided to the system. Now this software will give us the design values, and we have to reiterate our analysis. So if we analyze this data, you will see that stage wise, you will get a bending moment and shear force and bending moment and displacement diagram. In stage one, when the surcharge was applied, this is the bending moment. So you will see as we move down, the bending moment you will increase. In stage two, it was roughly around 20 kilometer meter only. Now it comes to 100, around 100. You can see. As per stage, the bending moment will be. This is the bending moment in construction stage. So this is the summary. Like for this diaphragm wall, the displacement is around, the deflection is around 28 So it is within the limits. So all the assumptions are correct. The maximum deflection as per the ODS shall be 35 and the bending moment here comes out at maximum 204.85 level. It is around 960 kilonewton meter. So at every level, as we move down the retaining system, we have a bending moment, shear force, for which now we have to design the our retaining system for the construction stage. I hope it's clear to everyone. This was the construction stage analysis in a Wallop software.
Gauravji, sorry to interrupt. We will have a tea break at 10:45. So before that, for a 5 minute, we will have query round because we have got
Okay,
received many queries. Okay. So till
okay,
that,
okay,
you can continue like 10:40 till 10:40. You can continue for 5 minutes. We will take queries, and then from 10:45 to next 10 minutes, we will have tea break.
okay, okay.
T and Y brick, whatsoever it may be.
Okay. So now we move forward. We have now done the construction stage analysis. Now we will come to the design of underground station permanent stage analysis. This is performed in mostly in StatPro software or sometimes in Midas Gen software also. This is a typical 3D rendered view model, which is prepared using FEM model, which I will show you just now. This is a typical cross-sectional view of STAT model. Here you can see the wall and the roof slab, concourse slab, and the base slab. Now, before moving on to the STAT, I will make you familiar with the loads and the load combinations as per the design basis report. So firstly, we will move to the material properties. In our ODS, we have defined that the structure has to be defined for 100 years of life. So as per that, we have defined the minimum grade of concrete so that there is no confusion later on. That the contractor, if he wishes to, can increase the grade of concrete, but this is the minimum which has to be followed. Like for inner slabs and beams and columns, it is M35. For outer slabs, is also M35, and then diaphragm walls, so tension pile, platform slabs all are M35 minimum grade of concrete. Then we move to the materials where the there is contact with the soil or water. Then it is the grade of concrete is M45, like the outer slab and then the diaphragm walls. This is the minimum cover requirement for 100-year durability. For inner beam slabs, columns, it is 50 mm. For outer slabs at roof, it's 50 mm. Outer base slab is 75 mm. Then outer cast in situ walls against formwork is 50 mm. Diaphragm walls is 75 mm. Tension piles, barrettes, compression piles is 80 mm. Then platform slabs, internal RCC walls, vent shaft walls, staircase slabs, UP, OT ducts is 35 mm. And where the underground station is in contact with rainwater or aggressive soil, which makes the condition severe, then the outer slabs is 65 mm, diaphragm walls is 90 mm, and then tension pile, barrettes, and compression piles are 95. Density, you all must be knowing 25 kilometer per meter cube for the RCC and 23 for the plain concrete. Reinforcement grade, we have to adopt FI 500. Density 78.5. For structural steel, all steel work shall comply with IS 800. Fire resistant period, which is very important. We have defined that like all the main elements of the station structures, roof slab, concourse slab, base slab, outer wall, columns, or any load bearing RCC walls, including fireman staircase and public fire escape underground structure, shall be designed for a minimum fire resist period of 4 hours. And all other elements like platform slab, vent shafts, UP walls, OT ducts, stub columns, and other non-load bearing RCC walls shall be designed for 2 hour fire. Now comes the crack width, which is very important in underground structures. The minimum reinforcement also is very important. It shall be minimum 0.125% of the cross-sectional area of the structural member on each face in each direction. Crack width shall be 0.2 mm for the all the elements which have connection with the soil, with have contact with the soil and the water, and for other internal elements it shall be 0.3. Now this is the minimum cover for crack width calculation we have also defined in our ODS, which is C minimum. You can see for M35 grade of concrete it is 45 mm, and for M40 and above it is 40 mm. Now comes the load as per DVR. Sorry. Now loads which has to be applied in the service stage model are these I have done in the highlighted in the yellow color. Dead loads, which is the self weight of the structure. then the superimposed dead loads, SIDL, which we usually call. Then comes the live load for the passenger movement and all, which comes under live load. Then comes the railway load, which is the movement of our rolling stock. Then comes the derailment load. Then comes the seismic loads. Then comes the construction by erection load. Construction loads are basically like during the construction, you on the roof slab, excavator is moving, so we you have to take the load for that also in our service stage model. Then comes the earth pressure. Then comes the lateral earth pressure, like or the uh, uplift, which will come in hydrostatic pressure. Then comes the surcharge load and accidental load. So in ODS, we have defined each and every load. Dead load is the cell weight of the materials and shall be calculated in accordance with IS 875 1987 Part 1. Then comes the SIDL load, and SIDL load we have vastly defined in which area what is the value of the load. Like in concourse area, for finishes it is 2.4, for partitions it's 1, for ceiling it's 1, for UDL imposed load. So we have provided this table. You can just have a look at this table. You will see that in the water tank or fire tank area there is 20 kPa load. In chiller rooms there is 10 kPa load. In transformer or substation room, it depends upon the uh, type of structure, it is 10, 15 to 20 kPa load. So each and every SIDL is defined. Then comes the railway load. Railway load is like this 17 tons of axle load divided it in 22100 length of the car. We can apply UDL also as we are doing static analysis. Then comes the horizontal train live load. Braking load is 18% of the unfactored vertical load. And then traction load is 20% of the unfactored vertical load. Footpath live load is 5 kPa. Derailment load is defined in our ODS. Like for a platform, station platform edge, a nominal load of 1000 kilonewton acting horizontally and normal to the platform slab edge over a length of 2.2 meter shall be considered. Wind load is not part of the underground station. Then in underground station, we do the seismic analysis. For seismic analysis, we do the racking analysis, and for that, a paper hashash paper has been defined, which I will later tell you in detail. We have to design for operating design earthquake and maximum design earthquake. Earth pressure we have to calculate. We have to calculate for both the cases, active and at rest. Surcharge, vehicular live load surcharge of 24 kPa on road station shall be adopted. And for building load surcharge, it shall be 60 kPa, or if the actual building load is there, then the value has to be considered that only. Then comes the groundwater, which will be a uplift pressure on the base slab. Also, there is one important aspect in this underground station. Like I have explained you the strut and veiler system. So the strut and veiler system has to be checked for one strut failure also, as mentioned in our ODS. But the load factor in this can be changed to 1.05 instead of the ultimate 1.5 in case of the one strut failure. Then the permissible vertical deflection, like the vertical deflection shall not exceed 25 mm, corresponding to 35 mm of horizontal displacement. So as per that only we do the iterations in our Wallop software that the deflection shall be in within the limits if suppose the deflection was exceeding, like the model which I showed you in Wallop, their deflection was 28 mm roughly. If it is coming 45 mm, then what we have the option, either we have to increase the number of struts or the cross sectional area of the strut, or we have to increase the stiffness of of our diaphragm wall or retaining structure by increasing the thickness. Then comes the flotation check. Flotation check is basically that all the vertical dead load shall be greater than the uplift force of the structure by a factor of 1.1. So these were all the load combinations, load cases. Now this is a typical FEM model, cross section of FEM model showing the all the load applications in the structure. Now I will explain you the STAD model. Or before that, Anilji, we can take the questions and then I will explain the STAD model in detail after the break.
Okay, so I'm going to read those queries. We have got lot number of queries. Uh, Mostly is most of the people are asking about economical, which method is economical, top down or bottom up. So I think
So that depends upon number of questions. So there is no straight answer to that.
is a factor which is governing case to case basis.
Yes.
So so someone is asking what is the cutoff level and its depth in D wall.
What is the
Cutoff level and its depth in D wall. I
depth of
think
the D wall depends upon the like the construction stage analysis which I have showed you. In if you will see the deflection diagram which I showed you, the toe was stable. So that means I assume 5 meter of D wall depth below the base slab. It was sufficient. If I will make 3 meters below the base slab level, then we will have a toe failure. So whenever with the deflection in the toe will be exceeding the permissible limit, then we have to increase the depth of the D wall. So it is basically a iteration. We have to hit and trial up to what depth our structure is stable.
thank you, Gaurav. And Visesar ji, don't worry. Whatever tolerances about D wall you are concerned about with, we will discuss in next webinar series on 19, which we have planned. And next query is from Ravinder ji. Water table data is defined, but no information about fluctuation of water table has been incorporated. This is a query.
No, for the construction stage method, we like for the return period of the construction stage is like 5 years. The construction work for in construction stage will continue for another 5 years. If you are assuming, then the water table for previous 5 years has been considered average of that. And for like service stage, we consider for 100 years. Whatever will be the water table for the 100 years, we will be considered. So that comes mostly at groundwater table only. In construction stage, it is taken for the return period.
Thank you. Next query is effect on structure if we use FE 550D in place of FE 500D, basically steel structure reinforcement.
That is, I think, not relevant to this presentation
It's a basic
Hello.
general.
Yeah.
because
Yeah.
if you are like from day one, if you are aware that you have to design with 550D only, then there is no problem. You can go ahead with design of use of 550D reinforcement, but the design shall be as per 550D only. You cannot do like you design with grade of steel as 500 and then you use 550D at site, then there will be a problem.
Thank you. Next is what is stub column?
Stub column is basically a column which don't have its own foundation. Like a column starting from a concourse slab to roof slab is called will be called a stub column. It is a floating
Thank you.
column basically.
Thank you. Next query is what if crack width is more than 0.2 mm at surface, but on making groove, it is not deep. Is the structure rejected?
That will not come under the design part, because as per design, if the crack width will exceed zero point 0.2 mm in the design, then you have to increase the reinforcement or redesign your section, and always make your crack width less than zero point 0.2 mm. And as per site, if it comes one point more than zero point 0.2 mm, then the matter has to be sorted by the site team.
Right. Okay. The next query is why couplers not staggered in underground structures? We are using coupler at the same sections.
Because the code allows that if you are using any mechanical, then 100% of that can be done. It is as per the codal provisions.
Good morning, everyone. Actually, the couplers, we have no options for staggering because it is a junction of D wall and slab, right? So where we have choice, we should have staggered. But where we have no choice, right? Because D wall is doing first, then slab. So we have to left the all couplers on the same level, same line. So normally we should do 10-20% if possible extra so that let it save some extra margin. But we don't have no choice.
Yes.
Perfect. Thank you, sir. Thank you. Participant, this query was replied by Sri Mahesh Sarin, sir. He's Chief Engineer Design. He will be interacting with you all at 12 after 12:30. So I think there is one more query. What are the design factors that decide the width and depth of the wall?
Width and depth of the wall. For the depth of the wall, I think already answered the question. And the
Yeah,
width
yeah.
of the wall is also a section basically designed. We start with the 800 mm typically, and if the section is not passing in ULS or SLS condition, then we have to increase the thickness of the diaphragm wall.
Right. I think these are the queries. I have finished with the queries. So we can now take a bio break for 10 minutes.
Yes, yes.
So we'll join at it's 12, 10:42. We'll join at 10:52 sharply. So all the participants are requested to please come back, have it bio break, and please come back at 10:50 itself. Thank you.
Okay, thank you.
Hello,
Yes, yes. Who is this?
this is from the CMRL design team. I'm a deputy manager, and
Yeah, yeah, please.
I have a question. Is Mr. Gaurav is available?
Yes, I am
Uh,
available.
yeah.
Yes. In analysis of the wallop, what you shown, is it having a pressure distribution calculated based on the braced cut, which is suggested by Peck in 1969? The pressure distribution of the braced cut is different compared to a retaining wall. Is it following that method?
No, there are different types of method. If you have seen in the wait a second.
I hope this replies your query.
No, no, no. He told to wait.
Participant, please keep your mic mute. Thank you.
Yeah, are you asking about this? There are like different methods of calculating the bending moment and displacement, like its subgrid reaction model, 2D finite at Wallop version 3, or this surcharge. We have different methods. Like for factor of safety calculation, it is Berlin Potts CP2 BSc handbook. You can choose either of them in this strength factor method.
Can we see the pressure distribution of the soil pressure distribution?
Soil pressure distribution is not there in the output. There is only bending moment and the deflection.
Okay, because
You can separately discuss, I think, this issue later on.
yes. Okay, okay.
Okay.
And one more thing is in permanent stage model, you are applying a triangular loading of the soil,
Yes, yes.
which is not correct for a braced cut, correct?
I will be explaining you the survey stage model shortly.
Okay.
Thank you, Gaurav. Thank you for the queries.
Hello, sir.
Yes, Mr. Surendra, is there anything you want to ask?
Yes, on
Yeah,
regarding this minimum reinforcement shown in the DBR, Mr. Gaurav,
yeah,
that's 0.125 it is mentioned.
yeah.
Uh, this is based on which class? Because our class says in 456.12 for slab. That
Okay.
is for gross area, but you have
So,
mentioned as a gross area for the both
Gaurav
the
are you?
phases.
No, it is mentioned in the IS 456 only for the slabs, Mr. Surinder. I will separately you the clause, and moreover, the basically the governing criteria for this only is the earliest thermal cracking also. So basically, it comes in the range of 0.17, 0.16 only. So at most of the times, this 0.125% is also not governing.
For the other side, distribution side of the reinforcement, this is
Then
governs.
yes, then it
That's
will
why.
govern. Yes, yes.
Because if you use 0.12 on both the faces, it comes 16 dia for a 1000 d wall thick.
No, it's 0.125. I will share you the reference, and it has been put in ODS after considering all the clauses.
Gaurav I
Okay.
think we can start.
Okay, sure, Anil sir, I will start. Now I will brief you all about the service stage model design. You can see like this is a 3D FEM model which has been prepared using STAT software. So I will briefly describe you out how the modeling is done and what is the property which we has to be applied and what are the support conditions, then the loading, then analysis and the output. So firstly, I will show you a 3D rendered view. As you can see here, all the elements are minutely modeled in this using the plates FEM model. Here you can see the wall, then the roof slab, concourse slab, and the base slab in the magenta color. And in the cyan color, you can see the columns and barrette below. Basically, if I show you in the cross section, this is a typical cross section. It must be not be clear because of the supports. So I will just take some of the elements. So this is basically a part of the model which I am showing for clarity purpose. So you can here see the all the plate elements. These ordered wall has been modeled as. I will request to all like keep your mic mute. Ritesh Anandji, please mute your mic. Here you can see all the plate elements. Okay. So we have to model the full model. Then after modeling, all the modeling has been done, then we come to the property. So property we define like all the thickness of the roof slab is 900 mm, then we provide the thickness of 0.9 meter. So each for each and every plate element, we have provided the property in the stat. You can see the concourse slab is 550 mm. Then the base slab is this is wall is 800 mm. This is permanent column 1.5 meter into 0.8 meter. This is again a permanent column. So all the after modeling all the plate elements, the uh, properties has to be assigned. After providing the properties, support conditions has to be provided. Support conditions for the base slab and the lateral D wall. So that has to be applied by creating a spring. So like what is a spring? We are defining the soil. So what is the as per the properties of the soil, E value and other things, we calculate the spring values which we defined in stat for the exact behavior of the soil structure interaction. So all the supports has been provided. After providing all the supports, then comes to the load cases, which I have defined, explained you as per ODS. All the loads has to be defined, which will be self weight, and then all the dead loads which will there SIDL, soil backfill load, the load above the roof slab, which you can see here in green. Okay, similarly, the live load on the concourse slab, which is 5 kPa. Here you can see in green, blue, sorry. Will be more clear. So live load on the concourse slab, train live load, then the lateral earth pressure. All the earth pressure has been applied to our retaining wall. Lateral pressure, saturated dry condition, vertical surcharge load. Then comes the lateral surcharge load, water pressure. Similarly, all other loads as per the outline design specification has been applied in this stat model. And then all the load combinations has been created as per the ODS. Then we do the analysis of the structure. Like for an example, I will show you what are the moments, how to view the output results in the stat. So this is a typical like uh, MX local bending moment diagram of a base slab. After application of all the loads in the STAT model, after giving the properties, we have now the design bending moments. Like X is the transverse direction. X is the longitudinal direction. So this is the bending moments in the longitudinal direction of the base slab. We can also see in the Y direction. And this is the transverse bending moment in the coming in the STAT model. So here you can see that the red portion shows the bending moment, the highest being at the edge of the D wall. And then subsequently it is changing from the like hogging to sagging and then again hogging. So from this bending moment results and the shear force results, we design the our components in the service stage model. So after all the application of loads, we get the bending moment values, shear force values, everything. Then we simply perform the analysis and design of the structural components. Now, design of any structural components has to be checked for both the conditions, which is the ultimate limit state and the serviceability state. So ULS includes the moment and shear capacity checks, where our bending moment M by MU ratio shall be less than 1, and the shear force also shall be less than the shear capacity. Then comes the SLS check, which includes the crack width and the steel stress and concrete stress. Crack width, as already told, I have already told you, it's 0.2 mm for the soil face of the structure and 0.3 mm for the inner face of the structure. After the crack width, it comes the stresses. Permissible stress in concrete is 0.5 FCK and in steel it is 0.75 FCK. Now I will just brief you about the typical reinforcement drawings of the main structural components. Firstly, I will go to the diaphragm wall. Now this is basically a typical drawing of a diaphragm wall, where can you can see the elevation and all the reinforcement here. Like if the at the top at the roof slab level, there will be more reinforcement on the earth face than the excavated face. And as we move to the middle of the diaphragm wall between the concourse slab and roof slab, the reinforcement will be higher in the excavated face. And then again at the concourse level, the hogging will occur, and then the reinforcement will be more at the earth face. Then similarly, between the concourse slab and the base slab level, the reinforcement will be more in the excavated face of the structure as compared to the earth face of the structure. Then we move to the slab and column drawings are prepared. This is basically a typical slab drawing in which the roof level drawing has been shown, in which all the reinforcement has been marked as per the design. You can see that at the column location, the reinforcement will be more, and at the D wall location, the reinforcement will be more. This is the shear reinforcement diagram. Generally, the reinforcement required at the column location is more. So, and it fails in punching also. So, local thickening, a capital or a column drop is provided at the column location and at the diaphragm wall location if required. In this case, you can see that at column location, there is a substantial increase in the thickness of the roof slab. It is 1300 more than the basic thickness required against the 900 at normal locations. This is typically column reinforcement drawing. This is cross sections of the columns. This is basically a drawing of a pile below the plunge column or a normal pile or tension pile. Now this was the all about underground stations. Any doubts till now? We can take up Anilji. Then I will move on to the boat tunnel. Hello.
Yes, yes, Guruji.
Shall I move forward to the boat tunnel part?
Yes, yes, please move on.
Okay, okay. Now after the stations, next we come to the boat tunnel. Now what is a boat tunnel? It is a tube-like structure bored through the soil with the help of TBM, tunnel boring machine, which connects from one station to another. This is a typical cross section of a tunnel. Now, what are the elements in a boat tunnel? Firstly, the most important is the tunnel boring machine, and then comes the segment lining. So, tunnel boring machine, how it operates, it's very important before we move on to the design aspects. So, I will provide you a virtual tour regarding the how the TBM operates. So, this is an earth pressure balancing machine, which will just so the dia of the TBM depends upon project to project. Like in DMRC, the internal diameter is 5.8 meters.
Gaurav is there any audio in this video?
Yes, yes, there is audio. It is not audible.
No, it's not audible. I think you have to allow the system volume, system audio to capture. MS Teams,
But
there will be option.
okay.
Total length of 95 meters.
Yeah, now it is audible.
With its rotating cutting wheel, the tunneling machine breaks the material from the tunnel face. The material is then transferred to the belt conveyor system in the rear of the shield via a screw conveyor, while the hydraulic cylinders press the machine forward continuously. The reinforced concrete segments, known as lining segments, are installed under the protection of the shield skin. When the ring building has been completed, the machine can push itself against the new tunnel ring and drill further into the soil. The 83-meter-long backup accommodates all logistic facilities necessary for the operation of the overall system. The working method of an EPB shield is basically made up of two phases: the tunneling phase and the ring building phase. During the tunneling phase, the cutting wheel, which rotates at a speed of up to 2.7 revolutions per minute, is pressed against the tunnel face with a pressure of up to 400 bar by means of hydraulic cylinders. 24 hydraulic motors drive the cutting wheel via a gear rim, developing a drilling torque of up to 38,000 kilonewton meters.
वॉल्यूम बढ़ाना पड़ेगा.
Under this high pressure, the disc cutters and cutting knives made of high-strength steel loosen the material at the tunnel face. If necessary, the soil can be conditioned with water, bentonite, or foam using the injection systems located on the backup. With the help of nozzles integrated into the cutting wheel, the corresponding conditioning medium is injected into the soil, which is pressed into the excavation chamber by the existing earth and groundwater pressure. For shield tunneling in non-stable soils, a loss in stability at the tunnel face is compensated by creating a support pressure. In the case of the earth pressure balance shield, the soil which was excavated by the cutting wheel is used to support the tunnel face. In order to reach a state of equilibrium, the support pressure is transferred by the hydraulic cylinders via the bulkhead to the soil, which avoids an uncontrolled penetration. The soil prepared in this way can now be transported from the invert area of the excavation chamber to a belt conveyor by a screw conveyor. The screw conveyor is driven by two hydraulic motors which have a power of up to 400 kilowatts. The quality of the soil taken from the excavation chamber is regulated by the screw conveyor's rotational speed, which is matched to the advance speed. The aim is to maintain a state of equilibrium between the quantity of soil removed by the screw conveyor and the quantity of soil accumulated from the shield's tunneling process. This guarantees optimum support for the tunnel face. The system must be able to react flexibly to the permanently changing geological conditions. Therefore, the current state is continuously controlled with the help of pressure sensors, by measuring the cutting wheel torque and the screw conveyor torque, and by monitoring the excavated material. When the tunneling phase is completed, cutting wheel and screw conveyor are stopped. Now the ring building phase starts in the shield area under atmospheric pressure conditions. A complete tunnel ring consists of several segments, called lining segments. These prefabricated reinforced concrete elements are produced with millimeter precision in a factory which is especially installed above ground for this purpose. Following quality control, they are then transported into the tunnel by mine cars. In the front section of the backup, the lining segments are lifted individually by a special transfer crane. It lifts them onto the segment feeder which transports the elements to the front of the tunnel. Here, the heavy ring segments are picked up and positioned by a hydraulically controlled crane arm, called the erector, using vacuum plates. The erector is installed on two rails and can be moved, rotated, and telescoped. Each completed tunnel ring consists of several segments, two lateral elements, and the key segment, which is installed last. The positioning of the segments always follows the same routine. The erector lifts the stone from the segment feeder. The hydraulic cylinders are then retracted from the corresponding installation point. The segment is positioned precisely, holding sight contact next to the previous installed ring, using a remote control. Now the hydraulic cylinders are extended again to secure the segment in its position and to subsequently bolt it into the previous ring. During this process, machine and tunneling personnel are protected by the shield skin against the earth pressure and any possible groundwater. In this way, the light segments are installed on each side alternately. The key segment, with its tapered sides, is slotted into position last and distributes the loads in the ring, completing the ring building. Subsequently, the next tunneling phase can start. The end of the shield, the so-called tailskin, is equipped with a circular tailskin sealing. This provides a seal between the sealed structure of the shield machine and the segment ring.
So from this, I hope it was clear that how the TBM tunnel boring machine operates. Now we will move forward, and now comes the segment lining. The salient features of segment lining is like the metro tunnel can be both in soft or hard strata and has to be lined with RCC. It is lined with a ring of RCC segments and concrete grout. There are total of 6 segments in one tunnel ring, including the key segment. Internal diameter of the tunnel is 5.8 meter in DMRC Phase 4 project. And then the width of the segment varies from 1.2 meter to 1.5 meter as per the convenience and the requirements of the contract. The thickness of the segment is as per the design requirement. However, for 5.8 meter diameter tunnel, it is usually taken as an adopted as 275 of thickness. Design life is 100 years as per ODS. This is a typical cross section of an tunnel segment ring. It includes the 6 segments you can see, including the key segment. Then the design of segment lining. Detailed studies and design are performed using 3D finite element modeling with the help of softwares like Plexus 3D or RS2 for the design segment, and to ascertain settlement of buildings and structures due to underground tunneling and excavation, which are above the ground structures. So basically, like for the underground station, I have explained you the software It is the Plaxis or RS2 software is similar, which enables soil structure interaction. And firstly, similarly as defined in Wallop, we have to move in similar stages. Firstly, we have to define our soil property. Then after defining the soil property, like first step one is the adding geotechnical parameters in the software as per the GIR, geotechnical investigation report. Like in this example, in the GIR, it is defined that from 0 to 5 meter, the parameters of the soil are so and so, and then in 5 to 14 meters, similar up to 21 meters, we have mentioned the parameters for the soil, which has to be input into the software. Then the material properties of the segment lining as per ODS. The concrete grade is M50. The modulus of elasticity is 35355 Newton per mm square. Then the grade of steel is 500. These are all the loads and load combinations as per the design basis report. The dead load, again, this is the loading conditions. Mainly it includes the load combinations, which I will show you. These are the all the load cases which have to be considered as per the ODS. The load case one will be groundwater table at the ground surface with uniform surcharge of 60 kPa. Then the load case 2 will be groundwater table at the ground surface with no surcharge. And then load case 3 will be no groundwater table with uniform surcharge of 60 kPa. Then load case 4 will be no groundwater with no surcharge. And load case 5 will be groundwater table at extreme water level with no surcharge. So basically, there will be a soil pressure, a surcharge load, and the groundwater table in this. These are the load combinations: DL plus IL, DL plus EQ, DL plus IL plus EQ, collision load, and accidental load. In stations also, I think I missed the racking analysis. In racking analysis, what we do, we have to calculate the free field deformation in a structure. It is similar for both a tunnel and for a station closed box structure. And from for that maximum deflection, we have to apply a load on the STAD model, or in tunnel in Plaxis, we can apply the maximum deformation itself in the Plaxis model. After application of all loads and load combinations, analysis is performed for the outcome of results in the Plaxis or RS2 model. And similar to that of underground stations, ULS design is done, which includes the moment and shear capacity check, and then the stress check and the crack width check. Now, these are the additional checks for the design of segments, like the stacking of segments. At the casting yard, segments are stacked like this. So the segment has the load for the stacking, a separate check has to be submitted for the cell weight of the above 5 number of segments for the bottommost segment. Then comes the lifting of segments. As you have seen in the virtual tour, the segment is lifted by the TBM. So a lifting of segment check has to be done also. Then the axial force of TBM operation, as the TBM move forwards, it will create a thrust to the already installed segment. So that axial force from the TBM vendor has to be considered for the additional check of the segment lining. You can see the hydraulic jack creating a thrust on the already installed segment line. Now comes the typical reinforcement drawing for the segment. You can see a segment. There is this plan of a segment, and this you can see a cross section. This is the developed view on intradose of segment, and this is on the extradose of segment. Similarly, for all other segments, segment 1 to 6, the drawing will be prepared. This is a cross section of a segment. Now in this, like the in the if the strata will be hard in the segment lining, the reinforcement generally comes lesser than that of the soil. It comes in the range of 80 to 90 kg per meter cube if the TBM is driven into the hard rock or hard strata. If the TBM is driven into the soil parameters are like uh, not hard, then the reinforcement in the segments comes around 100 to 110 kg per meter cube. And then these are some of the site photographs which you can see. Roof slab reinforcement is in progress. You can see here the lowering of the diaphragm wall. This is the plunge column and the casting of the concourse slab. And this is a site video which will show you that TBM crosses from all the residential area. This is a launching shaft basically. There is no audio in the video. This is the green arrow shows the tunnel being crossed from all these buildings beneath the buildings. So it is very important to like take care of all the minor settlements and at the above ground structures during the TBM operation. This is the alignment of phase 4 project. And this comes the station part. You can see the casting of the roof slab and the further ongoing of the project. This is in cut and cover method in which you can clearly see the strut and veiler. This is a casting yard where all the segments of the tunnel ring are casted. So that was all about the tunnel. Now we will move forward to the cross passages, which is constructed using the method of NATM. So design requirements of a cross passage. Cross passage, as per NBC 2016, first cross passage has to be provided not farther than 500 meter from the end of platform of an enclosed station or from the tunnel portal or from a mid tunnel exitway, and distance between the two cross passages shall not be more than 250 mm. And cross passage shall be a minimum height of 1200 mm in clear width and 2500 mm in height. This is as per NBC 2016. Now, typical drawings of a cross passage. This is a typical drawing of a cross passage with sump. So this is a connection between the two tunnels, TBM bored through tunnels. Here you can see there is a cross passage. It can be a circular and a box also. Here you can see a typical box type of cross passage with sump. Now, what are the components of a typical cross passage by NATM method? So construction of cross passage by NATM method requires the installation of primary lining, excavation, and installation of secondary lining. So primary lining consists of four-poling, lattice girder, shotcrete, rock bolts, and secondary lining is a permanent lining, which is a RCC structure. So first we will move to the what is a four-poling. So four-poling is in the diagram you can see it is a basically a support system for the excavation of the face of the uh, tunnel or a cross passage. Forepoling is a pre-excavation support of the excavation periphery. Any face shall not be opened without the forepoling. required in case of a large openings or a weak soil. These black dots you can see are the forepullings, and these are inclined members. Typically, steel perforated pipes with a diameter of 76 mm are installed with upwards angle of 10 to 15 degree from excavation circumference. Cementitious grout, more often admixed with sodium silicate, is grouted into the ground through the pipe to form a hardened canopy. The four-poling pipe shall extend at least 30% beyond the face of the excavation. Like this is the face of the excavation in the diagram which I've shown. Then the minimum length of the four-poling pipe shall extend the 30% beyond the face of the excavation. Then comes the shotcrete. Shotcrete is sprayed concrete of desired strength like M25 or M20. And shotcrete can be without reinforcement or with wire mesh or with steel fibers, SFRC. Then comes the rock bolts. Like after the forepulling has been done and the excavation has started, then comes the shotcreting part. And then, if required, if we are constructing a NATM tunnel or a cross passage in rocky strata, then if required as per design, rock bolt has to be installed. What is a rock bolt? Rock bolt is a long anchor bolt used for stabilizing rock faces. Rock bolt transfer the load from the unstable exterior to the confined and much more stronger interior of the rock mass. Rock bolts generally consist of a plain steel rods with the mechanical or chemical anchor at one end, at a face plate and nut at the another. In this diagram, you can see the anchor bolts and the radial bolts. The common type of bolts are SN bolts or Swellex bolts. Now, after the side excavation and side support has been provided, now comes the lattice girder. Now, what is a lattice girder? Lattice girder are proposed to install provide a stiff support for the exposed soil during excavation. Typical lattice girder are made up of three number of reinforcement of bar Fe 500 grade. Lattice girder can be of any structure steel also like ISMB or a UC section, or it can be made in the cross section shown below by joining the three reinforcement bars with the cross reinforcement. Now this will I will explain you construction sequence of cross passage. This video will here you can see the forepulling. Firstly, the forepulling has been is being done at the construction site. Forepulling and drilling has been done. Now first uh, excavation has been done and then a layer of shotcrete. Then comes the lattice girder or ISMB. Now comes the rock bolting. Then again a layer of shotcrete. Then again we move forward similar on a similar fashion. You can see as we further excavate, the forepole will extend furthermore 30% at least beyond the excavation. Then the bench excavation. Then lattice girder or ISMB at the bench part. Then invert excavation. Then again a layer of shotcrete. Then comes the permanent lining, final lining. I hope from this video construction sequence of cross passage was clear. Now this is the typical drawing, construction sequence drawing, which has to be issued at site, which again explain all the similar procedure which was shown in the video, like stage one, grouting and installation of 4 poles, grouting for ground movement through face and segments, probe drilling through segments and check for soil encountered along with any water seepage, installation of staggered double layer 4 poling with non-return valve in uh, both tunnels, installation of drainage drillings. In case of heavy water inflow, perform grouting through self-drilling hollow bolts with perforation. Then grouting zone should be at least 1 meter on all excavation sites. Then installation of temporary bracing inside the tunnel, like the segment rings are already constructed at the location where we have to build the cross passage. So for the access to the cross passage, the segment has to be cut from the pre-installed segment rings. So that will hamper the behavior of the segment rings. So for that, we have to firstly install the temporary bracings. You can see in this diagram, the temporary bracings in circular shape has been installed, so that when we remove the segment, the load will be distributed into these temporary bracings and our structure will be intact. So installation of temporary bracings in both tunnels before any excavation for cross passage is started. Then grouting zone should be at least 1 meter on all sides of excavation. Then comes the third stage, segment breakout. After like we have installed the temporary bracings, then we can remove the segment from the already casted segment rings. Ensure proper grouting grout zone before breaking of segment, then breaking through segmental lining of right hand side tunnel, then application of face sealing layer, then excavation of first 4 round of top heading with immediate application of spray concrete. So this is very important. Like after the segment is removed, first we have to excavate the first four heading, first 4 round of top heading with application of concrete layer. Then install outer layer of wire mesh, lattice girder, and apply first layer of sprayed concrete. Then apply second layer of wire mesh and sprayed concrete. Then after 4 rounds of heading has been done, then only we can start the one layer of benching. Excavation of one benching after 4 top heading excavation with immediate installation of outer layer wire mesh, lattice girder, and apply first layer of sprayed concrete. Then application of second layer of wire mesh and sprayed concrete at benching portion. Then similarly, next 4 rounds of top heading excavation with second benching. After four of heading, then one benching, then again similar procedure has to be performed. Then installation of steel frames, installation of permanent steel frames in cross passages, openings, application of waterproofing membrane on inside of temporary works and sprayed concrete, then installation of grouting hose and hydrophilic strips around passage openings. Then construction of permanent works, which will be the lining, permanent lining. Then after the permanent lining has been casted, then comes the removal of the temporary bracings. And the permanent lining will also have the important, like the connection of the tunnel segment of the bulkhead, which you can see the top left and top right corner, where the like cross passage is being connected to the tunnel segment. The thickness of the permanent lining is increase is more than the normal, because all the loads after removal of the temporary bracing and a segment has been removed, so all the load will now come to the junction of the connection between the segment and this bulkhead. So bulkhead has to be designed as per that. This is a final typical circular cross section which shows all the four poles, permanent lining, top heading, benching. And now comes the analysis and design part of this cross passage. So it is similar theory will be applied in this as per the stations which I have explained you in detail and in tunnel. Firstly, the geological model, then the definition of material parameter, then geological units, then overall construction sequence have to be inserted into the software like in Wallop or RS2, sorry, in Plaxis or RS2, and then the calculations. Then we have to check that the deformations and the ground settlement or the design of lattice girder, we have to evaluate our results. Like if the deformations are increasing, then we have to maybe increase the spacing of the lattice girder. Like we have assumed 1 or 2 meter of initially the spacing of lattice girder. If it is failing, then we have to increase the spacing of the lattice girder. We might have to change the type of the lattice girder, increase the thickness of the shortcut. So this all iteration has to be done, and then only we can achieve into the final conclusion of the uh, all the components like permanent and the temporary. So a similar FEM model in Plexus has to be prepared. Like this is, I have shown a typical cross section of a cross passage in which the soil has been modeled, surcharge has been applied, and then we will stage wise we will show the construction sequence. Like similar the sequence we have prepared, the same we will input in the software to get the desired bending moments and shear force for the design. So this is basically permanent lining design. All the load cases are similar to that of a tunnel. Load case 1, groundwater table at the ground surface with uniform surcharge of 60 kPa, and then groundwater table at the ground surface. All are similar to that of the tunnel. This is a typical cross section of a cross passage connecting the two tunnels, showing the permanent lining. These are the load combinations as per the ODS. This is the reinforcement drawing of a permanent lining. Here you can see this is the bulkhead, which I was telling that all this segment will be removed. So all the load of the previous segment will be transferred into this. This is the cross section of the. So any questions up till now? Basically, this was all regarding the stations, tunnels, and cross passage. Now I will take up the questions part.
Yes, Gaurav, we have got a huge a number of queries. So I will read one by one, and then we'll have participant also allowed to speak and ask. But first, I will read the queries which we have received in chat box. So, so some of the queries are basically related with construction methodology and related with construction aspects, which I will not read because on 19th of April, separate dedicated webinar is planned on the construction aspects. Those queries will be taken care of. Carried only the design aspects. Someone is asking whether this webinar is purely for civil. Yes, it is purely for civil. And one query I've got is a very lengthy question is that uh, does STAT provide bending moment contours, results tables, and torsion contours result tables separately, and doesn't add as per the wood and armor method, which we normally follow in practice for any particular load combination. And it is very cumbersome process where I have to add the absolute value of torsion with bending moment for a large number of load cases, which I want to avoid. This was a query from,
Yes,
I think,
yes. It was
yes,
query from.
Swapnil Wellsare, is that?
Okay, Swapnil, if you want to get the wood armor movement, then directly from the software, then you have to use the Midas Gen software. Instead, there is MX, MXY, MY. So, if you want to adopt for wood armor movement directly, then you have to use the Midas Gen software. Stad Pro doesn't have this feature as of now.
Okay, thank you. Next query is how much load means jack pressure, other forces should be added to the forces extracted from FEM analysis of TVM tunnel.
The jack forces for which the it has to be designed for the thrust has to be provided by the vendor of the TBM. It is separate for separate TBM. So that has to be provided by that, and for that, the designer has to design.
Okay, thank you. Next question from the same participant. What are most important governing parameters for TBM tunnel design that should be taken care of, say, in situ stress, load cases, etc.?
What is the critical, like there is only 4 or 5 loads only. The surcharge load is there. The depth of the tunnel is very important, because like if there is the tunnel is deeper from the ground level, then there will be ovaling effect, so that will reduce the pressure in the that will reduce the stresses in the tunnel. So all the parameters like soil condition, water condition, depth of the tunnel, these governs the design of the tunnel.
Okay, thank you. Next question from Mohit Oja. I think it is related to execution, but yes, design may also comment. What measures to be taken if steps of the slips are more than the permissible limit in a tunnel during construction? So, is there any step we can take?
I think that will be answered by better by the construction team, if anyone here.
Yeah, I said basically remedial measures. Yeah. So, in underground sections, should we use NBC or NFPA guidelines in DMRC? Basically, there is a confusion between NBC and NFPA. So, I think you should clarify.
As I already told that for the cross passages, we use NBC guidelines.
Earlier, we were using NFPA, right?
I'm not sure. I think Sarin sir
Yes.
maybe may inform like for previous projects.
Okay,
Hello.
this query, sir.
Yeah. Yeah. Actually, earlier we are using NFPA criteria, but later on NBC has given, even with consultation of all the concerned persons, right? Like the spacing of cross passes. So 250 meter is the spacing of cross passes, but first cross passes from station. This is the distance given by NBC. This is 500 meters, right? This is a change from NFPA to NBC.
Thank you, sir. Thank you so much. Because earlier it was, I think some participant had mentioned, earlier it was as per NFPA 130, cross passage spacing were having maximum spacing of 244 meter, which was there, which we have used in previous phases also. But now we are following NBC.
Right.
Someone is asking, please explain the reinforcement detailing of the segment with respect to the forces resisted by it. I think that has been
For
covered.
yes, for that you can refer the typical cross section of the tunnel segment, and if required, it can be shared separately.
Yeah. Mr. Raman Thakkar has asked, can the key segment be installed at the invert of the tunnel? First part of the question, and clarity on the critical position of the key segment may be given.
Key segments basically shall always be staggered. That is the first and foremost criteria. It shall not come at same location at every ring.
So one part of this question is ask whether we can put it, whether we can put the key segment in the invert of the tunnel or not.
Yes, I think it can be installed. There is no issue in that.
Though in DMRC we are not, I think, providing, we are avoiding. But yes, as per design, we can put.
Yes, as per design, there is no issue. I think.
Yes, yes. Aman, during execution aspects on 19th, we will clearly discuss the selection of key segment because there is a chart which we have to follow during selection, during ring building. So we'll discuss in detail.
Okay,
Someone
thank
has
you.
asked, someone has asked, four polling possible inside tunnel for cross passage construction. Is polling possible inside tunnel for cross passage construction? I think yes,
Yes, yes, it
we
is the
we
first
do.
requirement. Yes, yes.
Yeah, we do it. Someone has asked, like, can you kindly explain tunnel ring building and selection? We will explain in the construction basically webinar on 19th. Someone has asked, what is the minimum time required for stripping the formwork in arch portion of cross passage? It's a very specific question. Gauravji, am I audible?